In this video, I'll aim to answer the following questions. What is capturing? When does a closure implement the FnOnce, FnMut and Fn traits? And when should a trait bound of FnOnce, FnMut or Fn be used? Understanding the capture mechanism will make it easier to understand other closure concepts. When you create a closure, the compiler generates an internal struct for that closure. If the closure makes use of a value from its environment, then a field is included in the closure struct for that value. That value is said to be captured, and will be used when the closure is subsequently executed. The closure struct field will be one of the following, depending on how the value is used by the closure: an immutable reference to the value, a mutable reference to the value, or the moved value. This code demonstrates a simplified model of how the compiler implements a closure that captures a value by a mutable reference. The compiler sees that it needs the value of s for the closure, so it creates an internal struct containing a field to capture s. It captures s with the minimum access that still satisfies the closure usage. In this case, the closure only requires an immutable reference to s, because it's only printing its value. The compiler then implements the Fn trait for the closure, allowing it to be called. The call method only takes an immutable reference to self, because that's the minimum required to satisfy how the captured value is used. The call method implements the closure functionality, accessing the captured value as self.s. This code demonstrates a simplified model of how the compiler implements a closure that captures a value by mutable reference. The compiler captures s with the minimum access that still satisfies the closure usage. In this case, the closure requires a mutable reference to s in order to be able to mutate its value. The compiler then implements the FnMut trait for the closure, allowing it to be called. The callMut method takes a mutable reference to self, because that's the minimum required to satisfy how the captured value is used. Finally, this code demonstrates a simplified model of how the compiler implements a closure that captures a value by taking ownership. The compiler captures s with the minimum access that still satisfies the closure usage. In this case, the closure requires ownership of the value of s in order to be able to subsequently move the value back out of the closure by moving it into an option and then returning the option. The compiler then implements the FnOnce trait for the closure, allowing it to be called. The callOnce method takes ownership of self, because that's the minimum required to satisfy how the captured value is used. One of the reasons that closures can be confusing is due to their supertrait hierarchy, seen in this simplified extraction of the definitions in the file function.rs from the Rust core library. This shows that to implement Fn, FnMut must also be implemented. To implement FnMut, FnOnce must also be implemented. And, by extension, FnOnce must also be implemented in order to implement Fn. FnOnce does not have a supertrait dependency. The result of this hierarchy of trait implementations is that an FnOnce trait bound accepts closures that implement FnOnce, FnMut or Fn. An FnMut trait bound accepts closures that implement FnMut or Fn. And an Fn trait bound only accepts closures that implement Fn. The Rust book states that closures will automatically implement one, two, or all three of these Fn traits in an additive fashion. So each additional trait adds to the number of ways that a closure can be called. It then says, FnOnce applies to closures that can be called once. All closures implement at least this trait because all closures can be called. A closure that moves captured values out of its body will only implement FnOnce and none of the other Fn traits, because it can only be called once. So the FnOnce trait is implemented for all closures, but if a closure moves a captured value out of its body, then no additional traits are implemented for it. And a closure that only implements FnOnce cannot be called more than once. This makes sense, because obviously you cannot move a value out of a struct more than once. And when a captured value gets moved out of the body of a closure by, for example, being returned by the closure, this requires moving the captured value out of the compiler-generated struct for that closure. The book goes on to say, FnMut applies to closures that don't move captured values out of their body, but might mutate the captured values. these closures can be called more than once. So FnMut is implemented for all closures that don't move captured values out of their body. The description is correct to also say that closures that implement FnMut might mutate captured values, because closures that implement Fn don't mutate captured values, but do implement FnMut as a supertrait. Here's another way to say that closures that implement FnMut might mutate captured values, that mirrors the more explicit way that FnOnce was defined. A closure that does not move a captured value out of its body, but does mutate a captured value, will implement FnMut and FnOnce, but not Fn, because it can be called multiple times, but requires a mutable reference to a captured value. And finally, the book says, Fn applies to closures that don't move captured values out of their body and don't mutate captured values, as well as closures that capture nothing from their environment. These closures can be called more than once without mutating their environment, which is important in cases such as calling a closure multiple times concurrently. To summarize this, all closures implement FnOnce and can be called once. Additionally, if a closure doesn't move a captured value out of its body, then it also implements FnMut and can be called multiple times. And in addition to that, if a closure doesn't mutate a captured value, then it also implements Fn and can be called in ways that are compatible with an immutable reference, such as from multiple threads without the need for synchronization, or stored in another type and called from a method of that type where self is an immutable reference. So each additional Fn trait implemented on a closure increases the number of ways that it can be used. It's useful to understand what's happening when the compiler creates these implementations. First note that it's the trait method requiring least privileged access to the closure that implements the closure functionality. That trait method can then be called by trait methods with more privileged access, during which, for example, ownership is downgraded to a mutable reference, or a mutable reference is downgraded to an immutable reference. Looking at our earlier simplified model of how the compiler implements Fn to satisfy a capture by a mutable reference, the compiler must also implement FnMut, where the callMut method implementation wraps a call to the FnCall method, with the mutable reference to self being reborrowed as an immutable reference. And FnOnce must also be implemented, where the callOnce method implementation wraps a call to the FnCall method and the ownSelf is borrowed as an immutable reference. Also, our other earlier simplified model of how the compiler implements FnMut to satisfy a capture by mutable reference. The compiler must also implement FnOnce, where the callOnce method implementation wraps a call to the FnMut callMut method, with the owned mutable self being borrowed as a mutable reference. Consider this example of a function that takes a closure parameter trait bound on FnOnce, because the function will only call the closure once. It's called with a closure that moves a captured value out of its body, and so the closure only implements FnOnce. The trait bound on FnOnce forces the closure to be invoked by calling the FnOnce callOnce method. Here's another example of a function that takes a closure parameter trait bound on FnOnce. But this time we call the run function with a closure that does not move out a captured value, but does mutate a captured value. So this closure implements FnMut and FnOnce. The trait bound on FnOnce again forces the closure to be invoked by calling the FnOnce callOnce method, which in turn calls the FnMut callMut method that contains the actual closure functionality. If we change the function so that it calls the closure twice, then we have to change the trait bound from FnOnce to FnMut, resulting in calls to callMut instead of callOnce. If we left the trait bound as FnOnce, then the compiler would generate calls to callOnce for each closure call. But callOnce consumes the closure, and so the compiler would generate an error for the second closure call, because the closure would be consumed by the first call. This example demonstrates an event notifier type that stores closures as listeners for later execution. The closures are trait bound on Fn because they must be capable of being executed multiple times from an event notifier method where self is an immutable reference. The closure does not move a captured value out of its body or mutate a captured value, and so implements the Fn trait. If we try to use a closure that mutates a captured value, we would get a compiler error because such a closure does not implement Fn. The only way around this would be to change the trait bound to FnMut. But executing a listener closure through FnMut requires a mutable reference to the closure. To obtain this mutable reference, the event notifier self must also be a mutable reference. For the examples we've looked at so far, the self parameter of the trait method implementing the closure functionality has matched the captured value, meaning where the value was captured as owned, the call_once method took ownership of self. Where captured as a mutable reference, the call_mut method took a mutable reference to self. And were captured as an immutable reference, the call method took an immutable reference to self. But what happens in this case? Well, although we're forcing the closure to take ownership of the captured value by using the move keyword, the trait implementation criteria have not changed. The closure does not move a captured value out of its body and does not mutate a captured value, and therefore the compiler still implements the Fn trait with the call method taking an immutable reference to self. The last thing I want to mention is how to choose a closure trait bound. That decision should be based only on how the closure is being used. If the closure will be called at most once, then choose FnOnce. If the closure will be called multiple times, but not in a way that requires using an immutable reference, then choose FnMut. And if the closure will be called multiple times, but in a way that requires using an immutable reference, then choose Fn. Choosing the correct trait bound will ensure that no closures are excluded unnecessarily. A good example of this is the slicetypes sortBy method, which uses an FnMut trait bound for its closure parameter. Typically, when calling this function, you might use a closure like this, for which the compiler would implement Fn since it does not move out or mutate a captured value. But Fn is not the correct choice of trait bound, as it's overly restrictive. It would not, for example, allow a closure that mutates a captured value. Here, to count the number of times the closure is called, a mutable capture of a count value is required. So choosing the trait bound for sortBy should proceed as follows. Will the closure be called no more than once? No. The closure will be called multiple times because sorting needs to determine multiple element orderings by calling the closure each time. Therefore, FnOnce is not the correct choice. Will the closure be called multiple times in a way that does not require using an immutable reference? Yes. The closure will be called multiple times sequentially from a single thread in a way that is compatible with using a mutable reference. Therefore, FnMut is the correct choice. Fn does not then need to be considered, as it would only introduce an unnecessary restriction on what closures can be used with sortBy. Thanks for watching. And please like and subscribe so that you don't miss out on the next video, which is on the subject of the two hard things in computer science and Rust.